In this video, we are going to wrap up our module on metaprogramming by actually taking an in-depth example, a larger than usual example, that's going to be connected actually to our practice project. So we are going to look at a code example that uses both annotation and metaprogramming techniques together. And we are going to discuss at the end of this presentation how all of this could be applied to the practice project on the basic evolutionary algorithm. So let's get started with a simple program. So we're going to call our program metaprogramming demo. And we are going to go through a first version in the following slides that actually doesn't use metaprogramming. We want to just set the base here on the type of program that we want to modify and improve with metaprogramming. So this first baseline version is just the basic features of the program. Then we are going to add some capabilities to manipulate things a little bit more smarter, but we are going to still not use metaprogramming. And then at the end, we are going to pinpoint the flaws of this approach and replace it hopefully by something much better that is leveraging the techniques that we studied. So let's jump in. So we are going to have multiple Java files in this project, in this program. So the first one we are going to talk about is basealgorithm.java. So you can see the code for basealgorithm.java here on the right. Okay, there's not much to it. It's really like a small Java program. All it features is, well, we have a few, attributes here in a class named baseAlgorithm. All of those attributes, to make the example simpler, have the same data type, Boolean. So you see run level, stealth mode, and whatever as the names of the attribute, and all of them are initialized to false. Okay? So default value is false for all of our Boolean attributes. And then we have the only feature really of that base algorithm is that toString method that we override. And what it returns a string, obviously, that contains the name of the class, equal, then opening square bracket and closing square bracket at the end. And in between, well, we use a ternary conditional operator here to just say, well, if the run level flag, if the run level field is set to true, then in that string, I add actually a substring that contains the name of the attribute that is set to true, run level in this case, okay? Otherwise, that's what's after the colon, I put an empty string. So pretty much between the square bracket that follows the name of the class, we are going to get the name of all the attributes in the class, in this object, this particular object actually, that have been set to true. And that's it. Okay? So very simple code. Now what we are going to do is we are going to, this is supposed to represent an algorithm that does something useful in our application and that has 3 different Boolean attributes that serve as parameter, right? So now what we are going to do is we are going to try to build a little inheritance hierarchy around this concept of one class represent one algorithm. So let's move on to the next one. The next one we are going to call overAlgorithm.java. And you can see here that it extends base algorithm. So we have base algorithm being our current superclass, okay, the top class of our hierarchy, and then overAlgorithm extends it, is a subclass of base algorithm. It features the same structure, okay, so that means that we could have here one or more attributes that are all Boolean and initialized by default to false. Here the name of the attribute is overmode. So we try to make sure that we had different names for the attributes between the different classes. Okay, that's going to again make our job a little easier later on. You're going to see why. And then we also override this toString method. Since we're overriding this toString method that we inherited from base algorithm, we can call super.toString and have base algorithm, version of toString display all the flags, all the attributes that were actually set to true in the object that belong to the class base algorithm. And then below that, we're going to introduce a new line. Display overAlgorithm equals the same format with square brackets, and if the attribute overmode was set to true, then we display its name. So this is going to result in our object being capable to say, well, here are all the attributes that I inherited from base algorithm, and here are the ones more specifically that are true, and here are now the algorithm that I define in the class overAlgorithm, and more specifically the ones that are true. Okay, I think I said algorithm instead of attribute here. Sorry about that. So here are all the attributes that are true in the class over algorithm. Okay. So we have two classes right now. One inherits from the other. Let's continue. We're going to just make a small four class, I think, inheritance hierarchy. So this is a third one. We call it fancy algorithm. And fancy algorithm is exactly like over algorithm. It's a subclass of base algorithm. It has its own attribute with a different name called fancy mode, initialized to false, type Boolean, nothing new there. And then it also overrides the toString method, as you can see here. So it calls the toString method version from base algorithm, ask it to pretty much provide a string that describes all the attributes from base algorithm that are set to true in this particular object. And then we do the same thing for the attributes that are specific to the class fancy algorithm, yeah. So same pattern actually than over algorithm. The last class that we are going to define as part of this inheritance hierarchy is really fancy algorithm.java. And all we do here is, well, we say that really fancy algorithm extends fancy algorithm, okay? But other than that, so it's one level deeper, you know, in the inheritance hierarchy, but other than that, same kind of structure, right? This time we have two attributes. I told you we can have one or more, it doesn't matter really. So we just have two attributes here, type Boolean, initialized to false, same pattern than before. The toString method override the toString method provided by fancy algorithm, which itself overrides the toString method provided by base algorithm. And as we do in all the subclasses, we start by calling the toString method from the superclass. So it does its job reporting every attribute that was set to true from that class, okay? And if it's itself a subclass, guess what? It's going to call the toString from its own superclass. So we're going to go all the way up to base algorithm, and then we add what is specific to this class, okay? So we check in this current object if really fancy mode, which is one of the Boolean, was set, and we display it if it was set, okay? And actually, there's one thing missing here. I just realized we have another here attribute called not parameter field. So this one, we do not report anything about it because actually we consider it to be an attribute that is not going to be a parameter for this algorithm. So up to now, all the class, you know, pretty much all the algorithms that were Boolean that they feature were considered to be parameter of the algorithm. Well, here we wanted to make a quick exception. So we have a Boolean parameter, we have a Boolean attribute that is not a parameter. You're going to see later how we handle that, okay? But the bottom line is that this is just an attribute that we do not report when we prepare the string inside of toString. Okay, let's move to the next slide. So now we are done with this inheritance hierarchy. Let's talk about the class Meta Programming Demo, which is going to be our main class, the class that's going to host the main method of our application. So we have obviously our public static void main method in there. And all it's doing is it's taking some argument from the command line, which means that when you start this application as a command line, you are going to be able to specify a series of strings, a series of keywords after the name of the Meta Programming Demo class, and those are going to be passed to the main method through this parameter. Okay, so this parameter is an array of strings. Well, first thing we do, and we use a little bit of collection and generic notation here, but we define data as a variable able to hold a reference to an object of type list of string. This is how you read that if you have never seen that kind of notation before. So that just means that this is an object that's capable to manage a list, like think linked list, okay? And the elements of the list all have to be string. That's all we need to know right now about collection and generics to be able to get this to work. So then we create a new array list of string object. So that means that list was actually an interface. Okay, so we say we want a list, any type of list, okay, and we are going to put the reference into that data. But more specifically, when we create the object, we have to create an object from a class that implements the list interface. We cannot create an object from an interface, remember. So here, array list is one of the class that implements actually the interface list. So we create an object of type array list of string, and we pass as parameter here the result of calling the asList method, which is a static method of the arrays class. You can notice the uppercase A, so this is the name of a class here. And this method, what it does for us, it takes an array of string that is our arguments, that the main method receives automatically from the command line, and converts it into an array list of strings. So just we convert our array of string into an array list of strings so that we can use the array list iterators and things that make it easy to go and just iterate over a list of things. Okay, we don't want to mess around with the syntax of arrays pretty much. So that's the main reason for this line. Then we display a little bit of information for debugging purposes, a little bit more information. So what we're going to do is we're going to expect that the first argument that is passed to our program from the command line that we can find inside arg0, so this is where we find the string representing that first argument, we are going to consider this as being the name of one of our classes. So that can be Bayes algorithm, that can be a fancy algorithm, over algorithm, really fancy algorithm, okay? So that's what the user of our application is going to specify as first argument, the name of the class that they want our main method to create an object of. Okay, so here I have object ALG, algorithm. Okay, so object alg equal null. We are going to do a little bit of meta programming here where the command stands, and then we are going to display alg, which means that we are going to call the toString method that it implements. And it's going to display information about the object and all the attributes that we define into those different classes that the object contains and that has been set to true. Okay, so right now we have nothing really to set the attributes to true, so we're just going to display pretty much the name of the classes that this object represents. So if we have an object of class Bayes algorithm, that's just going to be Bayes algorithm, okay? If we have an object of class fancy or really fancy algorithm, then it's going to be displaying information about all the attributes in really fancy algorithm, all the ones that were inherited from fancy algorithm, and all the ones that were inherited from Bayes algorithm. So let's take a look at how we are going to make this happen. Here's the metaprogramming code. Okay, so some of it is familiar, like for example the class with a K equal class.forName arg0. So remember, arg0 is the name of the class that the user wants us to instantiate. So we are converting from a string that represents the name of a class to a class object, and that we store the reference of which we store in the variable here, class with a K. So that we learned to do in the previous slides, okay? What we didn't illustrate in the previous slide is that if you want to instantiate an object and you have a class object corresponding to the class that you want to instantiate, then you have a two-step process. The first step is you need to get a reference to a constructor, uppercase C, object. So the constructor object is like the class object in a way. The class object is supposed to represent all the information about a class, a given class, and make it available for runtime manipulation. Well, guess what? The constructor object represents all the information available on a constructor of a class and allows you to call methods on it and do some metaprogramming steps on it. Similarly, there is a field, uppercase F class, that contains which objects contain all the information for a given field in a given class, and we have also a method, uppercase M class, that does the same thing for methods. Okay, so these are the main classes in the metaprogramming API. You objects to represent a class, objects to represent a constructor, a method, or a field. So here we obtain this constructor. It's a kind of an easy simplified example because there's only one constructor in our 4 classes, okay? And that constructor is actually the default constructor that takes no argument. So it's really easy to call get constructor on the class object representing, for example, Bayes algorithm, and you obtain a handle on its constructor. And then once you have that, you can call a method called newInstance. And the syntax is a little bit weird here. I'm not going to get into the detail, but pretty much you are telling here that you want a certain data type to be returned to you. Okay, in our case, alg was defined as a reference to object, so we specify object here, and we get a new instance of our class, pretty much object, that we store in alg. So at this point, if the user specified as parameter, as argument on the command line, as first argument on the command line, the name Bayes algorithm, So the string here in arg0 would represent Bayes algorithm. We would get the class object for the class Bayes algorithm, so we would be able to find it because the class exists. And then we would ask that class object to get us a constructor. It would give us a basic default constructor with no argument that exists in Bayes algorithm. And then we would call it to create a new instance of Bayes algorithm and store a reference to it in alg. Okay, we have to use a try-catch block because, for example, the class here, if the class name is misspelled, we are not going to find it, so we are going to get an exception, okay? So that's why we have a try-catch exception block here. And then once we are done, if we successfully were able to get this new instance, then we tell the instance to display itself, which is going to cause it to execute its toString method. So that's it for the baseline of our code. So it has nothing to do with metaprogramming right now. We are just using inheritance. We're using polymorphism. Okay, we are overriding that toString method. So we're using a bunch of stuff that we covered in our review of Java object-oriented programming techniques, basic object-oriented programming techniques. And now what we want to do, well, we want to add the second feature of our code, which is after the user specified the name of one class at the command line, we want the user to be able to specify one or more names of attributes that are found in that class or in one of its superclass, and we are going to set those attributes to true in the object that we just created. That is our new feature, okay? So let's take a look a bit more in detail. So how are we going to get this done? We are going to add a parse method to each of our 4 classes. Okay, the role of that parse method is going to take a string as parameter and look up in that string actually to find different name of options that were passed on the command line by the user. And every time this method finds an option that matches the name of an attribute that has been defined in that class, then it's going to set that field, the corresponding field, to true. Okay, so by default, all of our Boolean attributes are false. We are going to give a string to parse that contains some of the name of those attributes, the one we want to set to true, and the parse method is going to get that done. It's going to set them to true on the object on which it is invoked. Okay, so just to get a concrete example, if I invoke my program by typing at the command line Java metaprogramming demo over algorithm, so that's the name of the class, right? And then over method, well, I expect my program to create an instance of over algorithm, and then I expect that instance of over algorithm to set the over method attribute to true, because that's the only attribute I specified here. And all over attributes that have been inherited or whatnot are going to remain set to false. So let's take a look at the code. Let's see how we can modify our Bayes version of the code to do this. So let's start with Bayes algorithm.java. So the first part of Bayes algorithm.java is going to be exactly the same. Here are our 3 attributes that we defined, 3 Boolean attribute initialized to false. Here is our toString method. Nothing has been changed yet. Okay, so next we are going to add to that Bayes algorithm class a parse method. And here's how it's going to look. So protected void parse, okay, protected because we want it to be accessible to potentially subclasses, but we don't want to make it a public method. And then we are going to say, I take as parameter a list of string, that is all the options that were specified by the user as a command line. So all the keyword like, over mode, run level, stealth mode, whatever, every name of attribute that might have been specified when running the program. And then what we do is we iterate over that list. Okay, so for each string OPT that represent one of the options in the list of string options, okay, we compare this OPT to the name of one of our attributes. So in the case Bayes algorithm, we have run level. If the name of run level is mentioned, then we set run level to true. So if it's mentioned several times, we just set run level several times to true. It's not a big deal, okay? If the name that's mentioned is stealth mode, then we set that attribute to true. If the name that's mentioned is whatever, we set that attribute to true. So those 3 strings here have to match exactly, if I go back one slide, the names of the three attributes that are defined in Bayes' algorithm, okay? That's a must. If they don't match exactly, then your code is wrong, okay? So, and we expect also the user to type exactly those names, you know, as a command line if they want us to take their input into account. So here's the parse method for Bayes' algorithm. Not too complicated, okay? Now what we're going to do is we're going to implement the same parse method in our other subclasses of Bayes' algorithm. And we are going to rely on polymorphism to make this all work. So let's take a look at how it's going to look exactly. Over algorithm, which is a subclass of Bayes' algorithm. So everything is as before, and we add a parse method. And the parse method is really similar to what we did with Bayes' algorithm, except that here we have only one attribute to worry about in the class over algorithm. So there's one comparison in the for loop here. And then because we are a subclass of Bayes' algorithm, if we have an object of class over algorithm, when we tell it to parse, you know, a list of options to see what attribute needs to be turned on, pretty much set to true, yes, it's going to take care of all the attributes that are defined in over algorithm, but it needs also to call the superclass version of parse so that it can take care of all the attributes that were defined actually in the superclass. Okay, so that's the only trick here. So that's basic inheritance and polymorphism. Okay, so we have code that's going to be able to parse all the attributes throughout the hierarchy of inheritance that we defined. Similarly, fancy algorithm, nothing new there. Okay, same as before for the definition of attribute and the definition of toString. Parse method also calls super.parse just like for over algorithm. And then it iterates, and there is only one attribute that we have to worry about that's defined in fancy algorithm. This is fancy mode. And so we do that. So exactly the same job done in over algorithm, fancy algorithm. Now I go to really fancy algorithm, the one that is one step lower in the inheritance hierarchy. Still, the same logic will apply. Okay, so we still call the parse version of our superclass. We iterate over all the options, and you will notice here that we had two attributes defined in the class really fancy algorithm, but we care only about one of them that we allow the user to set to true by using this command line, you know, feature that we have. Okay, the other one, it's not listed in toString, and it's not actually something that we can set to true by the command line. So it's really just an internal parameter of the class really fancy algorithm, not something that is exposed to that mechanism of option setting. Metaprogramming demo will be also a little bit modified. So everything you see so far on the screen is the same. Okay, so didn't touch that. The way that we instantiate our object is also mostly the same. So actually the try-catch block is exactly the same. But the difference here is once we have instantiated our object, instead of just going to the println and displaying it via its toString method, we have an extra step here, which is we take the reference in alg. We know it's going to be at least a Bayes algorithm or an object of a subclass of Bayes algorithm. So we cast it to Bayes algorithm and call the parse method. So the two steps for calling a method, okay, at runtime, one, we make sure that the class here actually provides us the parse method. It does. And then we look at the object and we call actually the parse method in the object. So if the object is of class really fancy algorithm, it's the parse method overridden in really fancy algorithm that is called. Okay, it's not the one up there in Bayes algorithm. So I refer you back to what we covered in inheritance and polymorphism reviews. Okay, so this is going to allow us to get all of the attribute parse. So if we create an object of class really fancy algorithm, no problem. We're going to parse it, and it's going to look for all the attributes for the class for really fancy algorithm, all the attributes for the fancy algorithm class, and all the attributes for the Bayes algorithm class, and set them to true if they are mentioned here in actually the data that we got from the command line. Okay? So what's next? Next version is going to introduce metaprogramming into this mix. Okay, so what we want to do with metaprogramming is we want to get rid of this cut and paste right now that exists between the parse method. They are very similar to one another, all right? And this is annoying. This is annoying because the first thing you learn to do with like inheritance and techniques of the sort is to factor code. You don't want to repeat yourself. That's the DRY principle. Don't repeat yourself. That is so dear to most programmers, okay? But here we are okay because we repeat ourselves, but we repeat ourselves with code. And this code is not easy to factor if you don't have meta-programming techniques. So we are going to kind of treat our code like data, and we are going to be able to factor things even further. We're going to be able to write a single parse method, okay? We are going to write it inside the superclass, the top superclass of our hierarchy. Actually, we're going to add one class before, you know, on top of a Bayes algorithm that's going to just contain the logic for that parse method. And then we are going to make it so that it can apply to every class by looking up at runtime the different types of attributes that we want to actually allow the user to set to true via the command line, okay? So that's pretty much our goal here. So just to summarize what's wrong with our design so far, highly repetitive code in all of those parse methods. How are we going to solve this? We are going to use annotation to mark the fields, the attributes that are meant to be option. Remember that in one of our class, we had 2 attributes defined, and only one of them was meant to be an option that would be displayed with toString, and that would be actually potentially set to true in the parse method. Well, so that means that we need to distinguish between the attributes that we want to parse and the one that we do not want to parse, okay? So to do so, we are going to define our own annotation, and then we are going to define that parse method, the new parse method that I already mentioned. So instead of having a bunch of copies of parse method, a bunch of definition of parse method overriding each other, we are going to have only one implementation in a top superclass, and that's it. And that's the one that's going to be called and do the job on any object, no matter what class it is an instance of. All right, so let's see how we're going to get this done. Let's start with defining our new annotation. So we have a new file, experiment_parameter.java. It defines the annotation at experiment parameter. So we have here the code to define the annotation. This annotation doesn't really need to do much, okay? So we don't have any field in it. We don't have any need to define a special constructor. We use just a default constructor, no arg. We really have nothing at all in it. It's just there to allow us to tag some of our attribute in those 4 classes in our hierarchy and mark them as, okay, this attribute represents an experiment parameter, so you should be able to set it to true via the command line. Okay, so the syntax here, public at interface experiment parameter, you should be familiar with this. We apply 2 meta annotation to our new annotation. The first time allows us to specify that we want this annotation to be available at runtime, and this is essential because our code is going to look for the attributes that have been marked as at experiment parameter attribute. And it's going to do that at runtime. So if the annotation is not available at runtime, there's nothing we can do. And then we are going to narrow down the usability of our annotation by saying that it only applies to fields. So we are going to prevent other programmers or ourselves, if we are making that kind of mistake, to apply the annotation to, say, a method or a class or something like that. Okay, so that makes sense. If you know that your annotation is meant only to apply to certain fields, you want to use the meta annotation at target to restrict that. And that's it for our new annotation. So let's see how we're going to use it. Let's take a look at basealgorithm.java, always to start with this one. So what's different? The first thing you will notice is the 3 attributes we define in the class that were each, used to as experiment parameter. We explicitly mark them, tag them with the at experiment parameter method. Okay, so we prefix them with that annotation. Sorry, I think I said at experiment parameter method instead of at experiment annotation. So we prefix them with that annotation to mark them as, okay, these guys need to be things that you can set up, with the command line, that you can set to true with the command line. Then we removed the parse method. We lost the parse method. We don't need it anymore. we are going to replace it by something better. And then we have our toString here that is pretty much still the same, okay? And then we're going to actually extend a new superclass. So we add a class on top of base algorithm, a superclass to base algorithm that we call overload. And this is where the parse method is going to be defined. This is where all of our classes starting with base algorithm are going to inherit it from. Let's take a look at, so one more thing that I should say, I'm not going to review over algorithm, fancy algorithm, and really fancy algorithm, and like those over class, because the modifications are exactly the same. All we do is mark with experiment parameter all the attributes that are relevant. So we are going to skip one in one of those classes, the one that was not displayed into string and not parsed in its parse method. And then we're going to remove the definition of the parse method in all of those classes as well. Now, moving on to metaprogramming.java, we are going to have to modify it a little bit to account for that overload class. Okay, so you see everything is the same except here, overload conversion, so that we can call parse, because parse is not going to be defined anywhere but in that overload class. So if we have a reference of type overload, then yes, we are going to be able to call parse, and then we are going to call it on a specific object that is probably an instance of base algorithm, fancy algorithm, or one of the 4 classes for sure. And now here goes our new class, the new superclass, that we want to add to our hierarchy. So the only thing that's going to be usable from the outside in that class is that protected void parse method that takes, the same kind of parameter than before, a list of string that represent option. And then we have 1, 2, 3, 4 helper functions, helper methods that are private to overload. So that means that the classes that inherit from overload, base algorithm and all its subclasses, are going to be able to call parse, but nothing else. And those 4 methods are just used, for us to simplify the implementation of parse and decompose it. So you can see that the first thing we do in the code for parse is we pass our list of options to parse recursive, which is one of the methods we're going to write. And we pass also the class object corresponding to the class of the object on which we were called. So obviously, if you have an instance of, for example, fancy algorithm, and you call the parse method on that instance of fancy algorithm that it inherited from base algorithm, which itself inherited it from overload, when you call des.getClass here, you are going to get a class object corresponding to the class fancy algorithm. Okay, that's the key. That's why it's going to work. All right, the parse method and the parse recursive method are defined in overload, but thanks to polymorphism, if we have a subclass, an object of one of the subclass, and we run that method, then the des reference to that object, so the class of that object is the subclass, whatever subclass it was, okay? So that's what's going to make it work nicely. You're going to see how. So now, let's move to the implementation of that parse recursive method. So from parse, we call immediately parse recursive. So the recursion is going to happen on this parameter, current class. So we check for termination condition. So if current class is null or the superclass is null, which means that we would be actually at a point where current class is a class object corresponding to the class object with uppercase O, well, then we stop. We have no business, going any further. There's nothing really, there's no way to go up for us in the hierarchy of inheritance anymore. And then at the end of the method, we are going to call ourselves recursively with the same options, okay, but with the superclass of our current class. So we are going to use current class to get a class object corresponding to our superclass, and there you go, we apply again the parse recursive job on that superclass. And then at the end, if it has one more superclass, then we go again and apply this job to the superclass itself. What are we going to do at each step of our iteration? Well, a little bit of display here for debugging purpose, but then we are going to say, all right, I need to call the method getOptionFields, which I'm going to provide in the next 2 slides, okay? We get actually here a list of field objects, okay? So we are going to iterate over a list of field objects. and we get all the field objects that correspond to our current class and that correspond to one of the options that is mentioned in that list of string option, okay? And then what do we do for each of them? So we have a try-catch block here, again, to intercept potential exception. We are going to set all those fields to true. So the way that you set a field to true, you have this method setBoolean that is of the class field. So on your field object, you can call setBoolean, say that you want to set that Boolean field that is located in this object to true. And that's the syntax. But before to do that, because the field is actually private, you need to set it to be accessible. And then once you are done making your metaprogramming operation and set it to true, you set it to be not accessible anymore. So you open the door, you close the door, in a manner of speaking, okay? So this is a syntax to actually set a Boolean field, a specific Boolean field represented by an instance of the field object in a specific object to a specific Boolean value, okay? And that's pretty much it. So we set all the fields that we get from getOptionField because it is the job of getOptionField to look up all the fields in my class that are marked with my annotation @experiment parameter, and then filter out of that list all the ones that are not mentioned as option. So when I get a list from getOptionField, I know that all those fields are existing in my class, have been marked as experiment parameter by an annotation, and are mentioned in the option that the user specified on the command line. So I can just set them to true. So obviously now we are going to take a look at getOptionFields, okay, eventually, and we are going to make sure that we see how we are going to implement this filtering. So let's take a look. GetOptionField, going to be easy. It's going to rely on the two last helper method that we defined, that we listed originally. So what it does, it returns a two-step process. So it returns first the result of getting all the marked field from the current class. So getMarkedField is one of our two last helper method. It's going to look at all the fields in the current class and identify the ones that have been marked by the annotation @experiment parameter. All the fields that have been marked by that annotation, I'm going to actually return an object of class field that represent them. So I'm going to return a list of objects of class field that represent all the fields marked by that annotation in my current class. And then keepOption is going to take that list and look at it to identify the fields which name has been mentioned in my list of options. And it's only going to keep those and return the list of all the fields that have been mentioned and that were marked as @experiment parameter. Okay, so we delegate the work here, a two-step process, create a list of all fields that are experiment parameter, then filter out all the ones that are not mentioned, and that's what we return as a result. The keep-only option, so we have two methods left, okay, keep-only option and getMarkedField. The keep-only options is already taking that list of field as parameter, that is all the fields from the current class that have been marked with the annotation. And what we do with them? Well, we create another empty list here, another empty list of field, and we are going to put from this list of field the element that are relevant into that new list of field that we end up returning. So it's filtering, right? So we iterate on all the fields from that list here, the parameter fields, okay? And we say, okay, I need to get the field name first. So there is a getName method that returns a string from the field class that gives you the name of the field. And once I have the name of my current field in that list, I go through all of the string in the option list and I compare to the name that I just got. And if the name matches, the field is mentioned in the list of options, I add it to my new list named list, which I return at the end. And that's it. So it's a basic filtering. We have a list, we pick the elements that match a certain criterion from that list, put them in a new list, return that new list. Last method we are going to discuss, last helper method, getMarkedFields. So you give a current class object to that method, and it's going to create an empty list of fields that it returns at the end, and it's going to populate that empty list of fields with all the field objects corresponding to the attributes of the class, of the current class, that have been marked with the annotation. So we call current class.get declared fields. It returns a list of field objects corresponding to all the fields in the class, okay? And then we iterate over each of those fields, and we are going to do, again, some filtering. So for each of the fields, we are going to say, get me all the annotations that have been defined, that have been used to tag that field. And then we get the field name, we display the field name, and we check one by one if any of those annotation is actually an instance of experiment parameter, which is our new annotation, right? As soon as we find that this field has one annotation of class experiment parameter, we add it to our list that we eventually return. So we go over all the fields, check all of their annotation, and if one of them at least is experiment parameter, we add it to the list. So we return the list of all the fields that have been tagged with our new annotation. And that's pretty much it. That's the meta-programming version. That's how it works. And you can see that, yes, the code is a little bit more complicated. During one of the lectures, a student asked, well, how can you say that this is easier, actually, or better than the previous version? Well, it's easier and better in the sense that your code is easier, actually, to maintain now. You have the same way that you are going to factor behavior that repeat themselves in several methods by using inheritance and polymorphism, you wouldn't argue that it's better to do cut and paste of the same method, in many classes, rather than using inheritance and polymorphism. Even for the first time you use inheritance and polymorphism, you are going to say, well, there are new concepts here, there's a little bit more difficulty. The truth is that it's new to us the first time we do it, but once we learn to do it, yes, it's a better approach. Same thing goes with metaprogramming here. There is a little bit of a learning curve at the beginning, okay? But once you understand actually the concept of metaprogramming and its technique, then you are capable to generate code where the specificities of the parse method have been correctly factored in one implementation of one parse method, so that if you ever have to modify the logic there in the future, there's only one part of your code to modify, as opposed to having to track down all of the subclasses of Bayes algorithm and all of the subclasses of Bayes algorithm and modify all of their parse method in the same manner, okay, which is a great source of actually potential bugs, okay? So that's pretty much where we stand. Now, what we're going to discuss about is how do we apply this to our basic evolutionary algorithm. And again, there are different ways to do that, okay? I've seen some of the design that some of the students came up with so far. They are widely differing designs, okay? I'm going to always use this base example of the three classes that I mentioned at the beginning: candidate, solution, population, and algorithm. And I'm going to use that as a way to illustrate how you could apply this technique, almost as is, to your basic evolutionary algorithm. But of course, if you have a design that is really different, then the trick is for you to reflect a little bit on what this technique is allowing you to do with all those parameters that we have in the basic evolutionary algorithm, and how you're going to be able to leverage it into your design. And if you cannot leverage it into your design, well, then explore an alternative design where you can actually leverage it, okay? That's the whole point of this practice project, is to constantly explore new design and new ways to re-implement the same algorithm in different manners. So here are some suggestions. So you notice that we have a lot of parameters, okay, in our class. Some of the attributes of our classes are going to be actually just private attributes that are needed for the implementation of the class, but we already have identified a list of attributes that are actually pretty much experiment parameters. For example, the maximum number of generation, the population size, the length of the binary vector that's stored inside of each candidate solution, the mutation rate, the crossover rate, and so on and so forth, okay? So this is obviously what this example I used in the slideshow was meant to help you with. It was meant to show you how you could manage in a meta-programming style type of way all those parameters and the ability to set those parameters to certain values from from a string that comes maybe from a text file, a property file, or comes maybe from the command line. Okay, I really don't care which way you go at this point. But that's the idea. The idea is that you have some user input that specifies the parameter values, and then you want your classes to adapt and set the parameter based on that. So I encourage you to use that @experiment parameter annotation to mark actually the attribute that should be configured via a configuration file, a property file, or just a command line. And then what you can do is you can do things such as, for example, if you have a class like candidate solution, one of the way to extend further our basic evolutionary algorithm that is not too complicated is to say, instead of my candidate solution working on binary vectors of fixed size, I'm going to have them work on integer vectors of fixed size. So you would have to have an extra parameter that say, for example, my integers can have values between 0 and n. Okay, so this is new because with a Boolean vector, the range was always 0, 1 by definition. Here you can specify the range, and you can modify also a version of 1max. So you can, if you had a class, fitness function pretty much, and you subclassed it into 1max. Now you can subclass again 1max into I don't know what to call that fitness problem, maybe nmax, which is going to be the integer version of 1max. So instead of summing all of the element of your binary vector in the candidate solution, you're going to sum all the element of your integer vector in your candidate solution. And if the length is 10 elements and you set the maximum value for each integer at 20, well, then what you're trying to reach is an optimal fitness of 200, okay? Which means you reach the max value on each of the element of your candidate solution vector. So 20, 20, 20, 20 in this example. So what you can do is you can have similarly a class candidate solution, two subclass candidate solution binary, candidate solution integer, and you can use obviously those property files, those experiment parameter systems to tag in each of them the different parameter that they need. Okay, for example, the candidate solution integer class introduce a new parameter in our experiment, which is a range of value that is allowed for each of the integer in the vector inside the candidate solutions. Okay, we didn't need that in candidate solution binary. So we are going to just add it to candidate solution integer, mark it as an experiment parameter, and then using the techniques that we covered today, you can have this class, parse pretty much the property files, the text configuration file, or the command line strings that were passed to find the value that was set by the user for that specific parameter. Okay, so that's just one of the suggestions. Obviously, we could do the same with population, introducing, for example, new selection schemes, and we could do the same even for the class algorithm, that is kind of like our central class that pilot all the steps of the algorithm, if we decided to move away from a steady state evolutionary algorithm. When I introduced our evolutionary algorithm that we're using for this project, I mentioned to you very fast and very discreetly, oh, by the way, this is a steady state version. Well, there are other versions. The problem is implementing different selection scheme, implementing different modes for the genetic algorithm, for the evolutionary algorithm, like from steady state to generational. This is something that, yes, it would be great to do that. It would be a nice exercise, but it requires me to even inject more domain-specific knowledge about evolutionary algorithm in those lectures. So I'm not going to push that on you because that's not your main focus in this class. So for that reason, I'm going to suggest that the modification that you use to actually test your this technique that we describe in this lecture on your practice project is instead, to integrate an integer vector in the candidate solution instead of a binary vector, because that is something that you can do without having to read more or learn more about evolutionary algorithm. Okay, it's really simple. We can generalize 1max that worked on binary strings to 1max working on a string of a series of integers. That's not a big deal, and we can do the same with candidate solution without learning new techniques. Okay. All right, and this is pretty much it as far as suggestions. So again, very important for those practice projects. Don't hesitate to share your design on the forums with other classmates, to use other classmates to discuss, how you can get yourself out of an impasse if you reach an impasse in your design. At this point of the course, I will allow you also to share the code on the forum. So if you want to start sharing code on the forum, go for it. I just ask that you contribute more than, here's my code, can somebody fix it for me? Because that's really not contributing anything. But you can share your code if the purpose is to provide to other classmates, something concrete to read and to maybe modify and to maybe investigate, okay? That's actually constructive for learning. And then I also invite you to come to Office Hour with your practice project, but the TA that we have this semester is going to also manage essentially the practice project. So he has multiple sessions. I think he has something like I don't remember if it's 8 or 10 hours of online session every week, during which you can join using Blackboard Collaborate on Canvas, and you can meet with him to discuss actually your practice project, show him your code, have him review your code, make suggestions, and so on and so forth. Okay, that's your primary point of contact, I would say, for getting an outside view on your code here. All right, and we are pretty much done with this presentation. So I'm going to wrap it up now. And if you have any question, don't hesitate to, again, use the forum, contact me directly, come to my office hour. I will be glad to assist you further.